So in this video, I want to go through a couple of the key concepts that I talked about in our last class on Thursday. And the key focus here is a couple of things that came out of section 6.2 and also what we've been doing in section 7.1 as some of the key concepts that we're going to use over and over again for the rest of the course. And so what I had said in the class was I'd like you to make sure that you are very, very comfortable with in chapter 6, section 6.2, the exercises for section 6.2. Please make sure, work through questions 57 and 58 that you see here. They bring some very, very important concepts to light with a relatively simple example, as an example that can be powered to a much more concrete and to a much more detailed level, as we'll do in subsequent classes and chapters. The second problem I wanted to make sure that you are very familiar with is in section 7.1, and in particular, questions 7 and 8. You were given a set of a population, just had a few observations in it. You were asked to make all possible sample sizes of 2. And it turns out there were exactly 15 unique samples or 15 different samples of size 2 that you could do out of that population. The questions then ask you to build a sample statistic for each one of those 15 samples. One time it was nothing more than the actual mean of the 2 values, and the other case your statistic became the range. And for both of those, you wind up with 15 observations, one observation of your statistic for each of your 15 samples. That observed, those 15 observations of your statistic will have their own sampling distribution. And we're going to talk about a lot of the characteristics of that sampling distribution as we go forward, even in this video. So with that in mind, I'm going to recap a couple other things that we did in class. This was all up on the board, but just I wanted to get it so that everybody had it for safety's sake as well. So here's where we started with the other day, and this is along the lines of problems 57 and 58 that I just referenced. Let a population X and a random variable of that population have a mean, mu of X, standard deviation, sigma X. We're going to take a sample. In this particular example, I'm going to do my sample is 3, a random sample, a random SRS of 3 items from the population, and I'm going to compute the mean of those 3 observations in my sample. I'll call that X bar, which in this case will be X1 plus X2 plus X3. Those are the 3 observations that I pull out of the population. Add up whatever that random variable value is, add them all together, divide by 3. And what we found out was, well, the expected value of this mean is nothing more than the expected value of what the random variable represents. And that's X1 plus X2 plus X3 over 3. That's the same as 1/3 times the expected value of X1 plus X2 plus X3, which is kind of what you see here. And remember, the expected value of a sum of random variables is nothing more than the sum of their individual expected values. Well, each one of these sample observations is coming from what? From the population. And so what would we think? Well, the unbiased estimator for what a value would be when we pull something out, one item out from the population, well, our safest bet is it will be mu. In other words, an unbiased estimator. That's the simple process that we see here. And so as a result, we're saying what? Well, the 3 expected values of X1, X2, X3, respectively, are all mu of X. I have 1/3. How many mu of X's do I have in there? I have 3 of them. What's that tell me? It tells me that the expected value of my sample mean is nothing more than what? The population mean itself. X bar is an unbiased estimator of mu. Excuse me, is an unbiased estimator of X. A little quick change there, because E of X is mu. Now, I can do a variance calculation. Hey, expected value of the sample variables. Same thing is true for the variance there. But one of the important points we notice, in this case, what are we doing? We're multiplying X1 plus X2 plus X3 all by 1/3 if you look at it. And so I've kind of rewritten the variance. An important point that you see over here in red is variance of a constant times our random variable is nothing more than what? The square of that constant times the variance of the original variable. So 1/3, bring it out. What's 1/3 squared? There you can see it written, 1/3 times 1/3 squared. times the variance of the 3 individual pieces. Moving back a little bit, 1/3 squared is 1/9. The variance of the random variables x1 plus x2 plus x3. What do we remember about variances? They add. So I'll have 1/9 times the variance of x1 plus the variance of x2 plus the variance of x3. Well, what's the variance of that random variable? Nothing more than the variance of the underlying population random variable. Just good old x. So what do I wind up with? My variance becomes 1/9 times what? 3 times the variance of x, my population random variable, 3/9, 1/3. My variance for the sample mean is variance of the original random variable from the population divided by 3, which turns out, by the way, to be the sample size. And so in general, I could say, if I have a sample size n rather than 3, nonetheless, my expected value for x1 plus x2 plus x3 plus blah, 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 plus x sub n over n, it's going to be equal to mu, the population mean. And the same concept that we saw over here with n equals 3, my variance is going to be nothing more than the variance of the original random variable divided by my sample size. And in turn, what then will my standard deviation be? Well, it's the square root of the variance of x divided by n, square root of the whole big thing. Square root of the variance is always the standard deviation of x, and divided by the square root of n. So what we see is, and hopefully you can see this as you move along, as we increase our sample size from the population, what's happening to our standard deviation? It's decreasing by a factor of 1 over the square root of n. We are tightening our variance. The variance of the sample mean will be less than the variance of the overall population. Very important points that are happening here. So that's kind of a prelude. What else are we going to talk about? Well, we talked in our last class about the concept of the population proportion. What you saw here is going to work perfectly with the concept of the sample mean in section 7.3. So really, maybe we were talking about some stuff from chapter 6. We actually just were doing a lot of the lecture of section 7.3, the distribution of the sample mean. Well, in section 7.2, what we did in class on Thursday is we talked about the sampling distribution of the sample proportion, p hat. Now, as we get started, there's a couple things we want to remember. This was also from chapter 6, as we started talking about the binomial distribution and the concept, remembering that when we do our SRSs, we are doing them without replacement. When we pull an individual out for a survey and measure something or ask them a question or whatever, we don't put them back in the population, grab our next person, who could be what? The exact same person we talked to. We certainly don't want to have a sample in which we're repeating people, or individuals or whatever. So we obviously do sampling without replacement. But what we saw was if the 10% condition was met, if our sample size was less than 10% of the overall population, then sampling with replacement looks very, very much like sampling with replacement, and makes our sampling look very, very much just like a binomial distribution. Every time we pull someone out from a sample, they either meet the criteria that we're looking for or they don't. In the binomial distribution, those probabilities from each individual are always treated as independent. Each individual, each entity in our sample is treated as being constant. When we don't have replacement, well, we saw way back when that those probabilities change just a little bit. And so we don't always have an 80% chance each time. After we grab the first person, our probabilities are no longer 80% and 20%. They're slightly different. And what we saw was with the 10% condition being met, those subtle differences in probabilities as we went kind of further into our tree diagram, as bigger our sample got, they tended not to matter. They tended to be relatively insignificant. And the translation for that, when all said and done, is when we're sampling with replacement, we can use the binomial distribution as an effective and good approximation for the results we're getting when we're sampling without replacement. In other words, the 10% condition allows sampling without replacement to effectively look like sampling with replacement, at least from a mathematical standpoint. The second thing we talked about was when our simple random sample, our SRS, meets the 10% condition, our binomial distribution can be approximated by a normal distribution when both n times p and n times 1 minus p are both greater than 10. N times p is the number of successes, n times 1 minus p is the number of failures. If we meet that condition, we've moved to a binomial distribution with the 10% rule. We will find that the large counts condition will allow us to take our binomial distribution and use it and model it with a normal distribution. And that's what we're going to work through just as we wrap up the last couple minutes of this video. So here is kind of the key summary point from section 7.2. When we're sampling, we typically look at each individual item pulled. That's a person, an answer, whatever it might be, or we're weighing something, measuring how old it is, how tall someone is. When we pull each individual item from the sample, we apply some type of judgment to it. That judgment is usually a success-fail judgment. Yes, you were within the desired range. My apple weighed more than 35 grams so that I could actually sell it. Whatever the condition might be, each piece of item, each item that we look at from the sample, each individual member of the sample, we evaluate it and we either kind of give it a success or failure concept. So what's that mean? We're essentially, n, the size of our sample, really translate into the number of trials. And for each one of these, hey, there's either a success or failure. We'll have some type of proportion of success. Now, remember what a binomial distribution is. We can say if x is binomially distributed with n trials and a probability of success of p, x is a random variable that represents the number of successes obtained in n trials. X is an integer from 0 all the way up to n. Remember, it's a discrete distribution. Only takes on, for the binomial distribution, just integer values from 0 to n. Each value of our random variable x represents nothing more than the number of successes obtained in n trials. Now, if we let p hat come from our sample and be nothing more than the number of successes divided by the number of trials, well, this random variable p hat is nothing more than the proportion of success in n trials. So let's say n was equal to 15 and we had 5 successes. We would have what? 5 divided by 15. Our probability, our proportion in this case, is nothing more than 1/3. So we can take a binomial random variable x and quickly, by dividing it by n, turn it into a sample proportion. Now, what's interesting about this is, okay, well, the expected value of the population proportion, well, it's the expected value of this lovely random variable we built. It's 1/n then times the expected value of x. What do we know about a binomial distribution? What's the expected value? Nothing more than n times p. So we have 1/n times n times p becomes p. What's this tell us? P hat, the sample proportion, is an unbiased estimator of the population proportion. Very interesting, very useful. Now, second thing, what's the variance of our population proportion? Well, it's very, very similar to the calculation we did with the sample mean a few moments ago. Look at how the random variable p hat has been written. It's x/n. Variance then of what? Hey, it's just a constant, 1/n multiplied by x. Remember what we did before. Constant, square it outside, times the population variance. What's that tell us? Oh, well, do you remember what the variance is of a binomial distribution random variable? It's n times p times 1 minus p. What do we have for a variance in that case? We'll have 1/n squared, and in our numerator we'll have n p 1 minus p. N/n squared will translate into 1/n, and so the variance of p hat will be nothing more than p times 1 minus p divided by n. And what's that tell us the standard deviation of our sample proportion will be? This exact same thing in square root form. So, what's this all have to do with anything? Well, it has a lot to do with just about everything. These two key concepts for the sample proportion can translate right into the following conclusions. When we have a known or assumed population proportion P and take an SRS of size n from the population, it turns out if the following two things are met, the 10% condition, allowing us to do what? Our sampling with replacement essentially models a binomial distribution, and we meet the large count condition, which then does what? It allows that binomial approximation to be turned into a normal distribution model approximation. If that is true, then the sampling distribution of p hat, our sample proportion, can be approximated by a normal distribution with a mean for the sample proportion equal to p, the population proportion, and a standard deviation, as you see here, the square root of p times 1 minus p over n. Remember, p hat, sample proportion, p with no marker, population proportion. Remember, they are different animals. But if you see this piece, this is the key to everything we will do in section 7.2. And a lot of these concepts, we work with proportion in section 7.2. A lot of what we've already seen here is going to be the sample mean in section 7.3. We're going to see that we have a tremendous volume of power that's going to be at our disposal to work through statistical inference.